Hello and welcome. Today, we will be discussing the fascinating topic of low-mass stars hosting giant planets. The core accretion theory predicts that this phenomenon is rare, but a recent study has challenged this long-held assumption. For years, scientists have believed that the formation of giant planets requires a massive core of solid material. However, this theory suggests that low-mass stars may not be able to produce such a core, which makes it unlikely for them to host giant planets. But the recent study has turned this theory on its head. The study has revealed that low-mass stars could indeed host giant planets, contrary to what we previously thought. In this video, we'll delve into the details of this groundbreaking study and explore its implications for our understanding of planetary formation. So sit back, relax, and let's dive into the exciting world of low-mass stars and their potential to host giant planets. The core accretion theory is one of the leading models for understanding how planets form. It proposes that rocky planets, like Earth, start out as tiny dust grains in a protoplanetary disk around a young star. These dust grains collide and stick together, eventually forming larger and larger bodies until they become planetesimals. Planetesimals can then gravitationally attract more and more material, eventually becoming planets. The theory predicts that low-mass stars, such as red dwarfs, are less likely to host massive planets because they have less material available in their protoplanetary disks. The amount of gas and dust available to form planets is proportional to the mass of the protoplanetary disk, and low-mass stars have smaller disks. Therefore, the core accretion theory predicts that massive planets around low-mass stars are rare. The theory also predicts that it is more difficult for a planet to become massive enough to attract a large amount of gas and become a gas giant. This is because the gravitational pull of a low-mass star is weaker than that of a more massive star, making it harder for a planet to gravitationally attract enough material to become a gas giant. In summary, the core accretion theory is a model for planet formation that suggests that low-mass stars are less likely to host massive planets due to the smaller amount of material available in their protoplanetary disks. This is because the amount of gas and dust available to form planets is proportional to the mass of the disk, which is smaller for low-mass stars. Additionally, the weaker gravitational pull of low-mass stars makes it harder for planets to become massive enough to attract large amounts of gas and become gas giants. According to the core accretion theory, planetary formation starts with small dust grains sticking together and gradually growing larger by colliding and sticking together. Over time, these larger particles come together to form planetesimals, which can then accrete more gas and dust to become fully fledged planets. However, the theory also predicts that this process is much more difficult for low-mass stars, since they have weaker gravitational fields and less gas and dust to work with. As a result, the theory suggests that low-mass stars are less likely to host massive planets, and that the planets they do have will be smaller and less massive than those around larger stars. While this may have seemed like a straightforward explanation for many years, a recent study has challenged this long-held assumption. The study, which was published in the astrophysical journal Letters, suggests that low-mass stars may be capable of hosting much larger planets than previously thought. This has significant implications for our understanding of planetary formation, and raises questions about the accuracy of the core accretion theory. The team of researchers who conducted the study are from the University of Warwick in the UK. They used data from NASA's Transiting Exoplanet Survey satellite, TESS, to search for giant planets around low-mass stars. Their findings challenge the core accretion theory of planet formation, which predicts that low-mass stars are unlikely to host giant planets. Instead, the researchers found evidence of giant planets around low-mass stars in about 10% of the systems they studied. This is a significant result because it challenges our understanding of planetary formation. The core accretion theory is one of the most widely accepted models of planet formation, so finding evidence that it may not be accurate in some cases raises important questions about how planets form and evolve. The team analyzed the data and found that 3 of the observed low-mass stars had evidence of gas giants in close orbits around them. This is significant because, as mentioned earlier, the core accretion theory predicts that gas giants should be rare around low-mass stars. The researchers noted that their findings do not necessarily disprove the core accretion theory but rather suggest that it may not be the only way that gas giants can form. They suggested that other mechanisms, such as gravitational instability or disk instability, may also play a role in the formation of gas giants. The implications of these findings are significant for our understanding of planetary formation. If gas giants can form more easily around low-mass stars than previously thought, it may mean that there are many more exoplanets out there waiting to be discovered. It could also mean that our current models of planetary formation need to be re-evaluated and updated to account for the possibility of gas giants around low-mass stars. Overall, this study highlights the importance of continued research in the field of exoplanet exploration and planetary formation. With new technologies and data becoming available, we are sure to learn even more about the diversity and complexity of the universe around us. The discovery of 15 giant planets around low-mass stars has significant implications for our understanding of planetary formation. These findings challenge the core accretion theory and previous research, which predicted that massive planets around low-mass stars were rare. One of the main implications of this study is that it raises questions about our current models of planetary formation. If the core accretion theory is incorrect, then we need to find a new way to explain how these giant planets formed. This discovery opens up new avenues for research into planetary formation and could lead to a better understanding of how planets form in general. Another important implication of this study is that it highlights the need for more observations. While the discovery of these 15 giant planets is a significant step forward, we need more data to fully understand how these planets formed. We need to know if these planets formed close to their host stars and migrated outwards, or if they formed further out and moved closer over time. Additionally, it is unclear whether the discovery of these planets is an indication that the core accretion theory is incorrect, or if it is simply an exception to the rule. More data and observations are needed to determine whether these giant planets are rare or if they are actually more common than we thought. In conclusion, the discovery of these 15 giant planets challenges our current understanding of planetary formation and raises important questions about how planets form. While this is just the beginning of a new era in planet formation research, it is clear that more observations and studies will be needed to fully understand the formation of giant planets around low-mass stars. In conclusion, this video discussed the possibility of low-mass stars hosting giant planets and the core accretion theory, which predicts that this is rare. However, a recent study conducted by a team of researchers from the UK using data from TESS has challenged this theory by discovering 15 giant planets around low-mass stars. The implications of these findings are significant as they contradict previous research and raise questions about how these planets formed. Further observations and research are needed to fully understand the implications of these discoveries. It is clear that this study has important implications for our understanding of planetary formation and highlights the need for continued research in this area. So, stay tuned for future updates on this fascinating topic.